Hey everyone, and welcome to video number 3, workshop number 1. Today we are going to review some problems from the first 2 lectures. So these would be problems dealing with molecular structure, constitutional isomers, formal charge, partial charges, and bonding. Okay, so let's go ahead and get started. Let's start with C3H9N. C3H9N. Okay, let's start with this one. So how can we draw our first isomer? Let's put number 1 here. Remember, when you're drawing isomers, constitutional isomers, or just drawing a molecular structure, the easiest structure you could possibly come up with is just to connect your heteroatoms and connect your carbons together in a straight line. Okay, so we're going to ignore the hydrogens. We don't really care about the hydrogens right now. We're going to plug those in at the end. Let's take our carbons and our nitrogen, and let's just plug them together in a straight line. 1, 2, 3, 4. Okay, so this is one potential structure we can have. Remember, nitrogen has 1 lone pair and then makes 3 bonds. Carbons should all have 4 bonds. So let's make sure our hydrogens add up. We have 1, 2, and then 3, 4, 5, 6, 7, 8, 9. Okay, so that works out. So here's our first structure, a 3-carbon chain with an NH2 on the end. So what's another structure we could draw? Let's look at number 2. So we have a 3-carbon chain here. Let's rearrange these in a different way. Let's take this nitrogen, take the amine, and let's put it on a different carbon. Let's take it and we'll put it on the 2nd carbon in the chain. Let's keep the same 3-carbon chain, but let's put that nitrogen out here on the 2nd carbon. And then that gives us 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens. That looks good to me. So this would be a unique structure. And this would be our second isomer. All I did was take the nitrogen and just move it to a different carbon. Now, could we take the nitrogen and could we move it to the first carbon in the chain? Could we put it on the left-hand side and draw something like this in the top left, or I'm sorry, in the top right here? Let's see. What if I took the nitrogen and I drew it here, connected it to the first carbon in the chain, and then filled in with hydrogens? Hopefully you remember that this is the same as number 1 here. It's just flipped over or turned so that the nitrogen is on the left side instead of the right side, right? It's the same molecule here if we draw the nitrogen on the first carbon or the 3rd carbon. So it doesn't matter which one we choose. If a nitrogen is on the end of either end of this 3-carbon chain, it's the same molecule. But if it's on the middle carbon, that's a different molecule. That's a different one, right? It's all about the connectivity. If you're ever confused, remember, work down the chain. C, 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 N, C, C, and then this middle carbon is connected to both an N and a C, so it's different connectivity. Okay, so we can't move the nitrogen anymore. We can't put it on any of this 3-carbon chain, so we have to break up this chain and try to connect it in a different way now. I always like to start with a straight chain and just test the isomers there, move things around. And once you exhaust all the options for a straight chain, then you can start breaking the chain up and looking at different combinations. So I think the easiest way to go now is to take the nitrogen and put it as a member of the chain. Put it right inside the chain between 2 carbons. Let's put it right in between 2 carbons. Okay, that means nitrogen would have 1 hydrogen on it. We would have 3 hydrogens on the carbon over here. 2 hydrogens on this carbon and 3 on the end. That would give us 3, 6, 7, 9. So that one checks out. Okay, now what's the last isomer we could draw? This one actually took me a minute to find out myself. You kind of have to think about it a little bit differently. We can't move the nitrogen between these 2 carbons over here, the first and the second carbon here, because it would be the same structure if we put the nitrogen over one more position. This is the same structure as 3, just flipped, right? It's the same backbone as 3, it's just flipped. So that would give us the same molecule. So what can we do that's unique and different? Well, we could connect all 3 carbons to nitrogen. C, 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 right? So we're taking this left carbon over here and we're connecting it to nitrogen. If you are stuck on these, always you can go back to your puzzle pieces. Draw out some carbons like this. We have 3 carbons like this. The carbons can form bonds in any way, 4 bonds, and then the nitrogen can form 3 bonds, right? And it's all about just connecting these puzzle pieces, connecting these single electrons in unique ways, okay? So you can always go back to these sort of puzzle pieces and think about them as pieces that you have to fit together in unique ways. So I'm just going to put CH3, CH3, CH3. That's a shorthand way to write out a methyl group. Just put CH3 rather than drawing all the unique bonds. So this would be our 4th isomer for C3H9N. These are 4 constitutional isomers, C3H9N. They all have the same molecular formula, but a different structure, different connectivity. Could we draw another one? Is there another one? Let me draw one that looks a little bit weird. Let's try to figure out if this is a unique structure or if this is one that's already drawn. Let me erase this here to get some space. Okay, so I drew a sort of strange looking molecule here with all these weird bond angles. It's kind of curves up, right? It looks a little bit different, but it doesn't matter how it looks. Remember, everyone can draw the molecules in their own way. You're perfectly fine to draw a molecule like this. Although once we get to future chapters and we learn about molecular structure in more detail, it might be considered wrong. But for now, we're just looking at the connectivity, right? So you can draw the connections in pretty much any way, but this structure here that I drew, it looks different, it looks unique, but it's the, it's the same as structure 1. It's a 3-carbon chain with nitrogen on the end. Let's work down the chain here. We have a CH3 in red, that's our first. Over on structure 1, there's our CH3. Next, we have a CH2. CH2. That's connected to another CH2. That's connected to another CH2. And then on the end, we have our NH2. And on the end over here, we have our NH2. So it's the same structure. It's just drawn differently. It's drawn crooked and flipped over, but it's the same structure. Okay. This is a very important concept to be able to understand whether or not you have unique structures written or whether it's the same structure. Okay. So if that didn't quite make sense, watch it again. You can even, if you have a molecular model kit, this can really help you out. If you build a structure and you can actually hold it in your hands, turn it around, flip it around, and see that it can be represented or drawn from any perspective. Okay. Okay, let's take a look at the second problem here. We have let's see, what's our second problem here? C3H6Cl2. So in this one, we have two chlorines. And we should remember, let's see, let me write this up here, C3H6Cl2. We should remember that chlorine has the same bonding pattern as hydrogen, right? The halogens have 7 electrons, so they form one bond. It's pretty much a hydrogen, but with 3 lone pairs, right? It forms one bond, but the halogens have those 3 lone pairs. Don't forget about those. Okay, so let's draw our backbone. Now, similar to the hydrogens, the chlorines, we don't really include when we draw the backbone of the molecule because it can only make one bond. So what I'm going to do to start is just draw 3 carbons right in a row because we have lots of different bonding options with these. Let's just start by putting them in the middle and connect them together, make our backbone. The next thing we should consider is the chlorines. This is what's going to give us our constitutional isomers, is where the chlorines end up and where the hydrogens end up relative to the chlorines. So to make our first isomer, let's go ahead and put both chlorines on the very end. Let's put them on the very end here. Now we should have 6 hydrogens left over, and it looks like we do, so that checks out. There's our first potential structure. The first one's pretty easy to draw because you just connect it in any way possible, and you have a structure, right? And then for the second, third, fourth, etc., it gets trickier and trickier because you have to check and make sure you're not drawing the same structure in a different way, right? So for the second structure, what can we draw? Let's keep with this carbon chain because we still have other options. And let's take one chlorine and move it over to the middle carbon. So now we have one chlorine on the end and one chlorine in the middle. This would be a unique structure that's different from the one above. Make sure all your hydrogens match up. We have 6 hydrogens, so that one looks good too. Structure number 3. Let's move that chlorine in the middle all the way to the other side. Now we have chlorines on opposite sides, and all of the carbons have 2 hydrogens for a total of 6, so that one looks good. And then what's our final option? How can we arrange these chlorines so that we have our final isomer? What's the last thing we could do? We can't put them both on the left because that's the same as putting them both on the right. But we could put them both in the middle. We haven't done that yet. Let's put them both in the middle. And then on either end, we have a CH3 and a CH3. Okay. Easy enough. Okay, all you're doing is writing down the backbone of the molecule. That's going to be your carbons, your oxygens, and your nitrogens. And then you're just going to move things around in unique ways until you get different structures. Okay, for our next practice problem, let's take this one. What we're asked to do is draw the isomer of the following molecule. So what we have here, this is called a cyclopropane. Okay, this is cyclopropane. So cyclopropane is a propane molecule that's in a ring or a cycle. Okay, propane is a 3-carbon chain, propane, and cyclo meaning circular or in a ring. Okay, so this is cyclopropane. What is the isomer of cyclopropane? Okay, let's bounce off in this direction and let's draw the molecular formula. Let's count up the atoms. We have 3 carbons, C3, 1, 2, 3, and we have 6 hydrogens, C3, H6. Okay, now let's bounce back this way and let's draw another structure for C3H6. Okay, so we have 3 carbons here. Let's draw these instead in a straight line, see what happens. H6, 1, 2, 3, 4, 5. Now we have 3 spots left over, only 1 more hydrogen. So what's going on here? Well, we have a double bond. Okay, we have 2 electrons left over on neighboring atoms, so this is going to be a double bond. Now, it doesn't matter if we put the double bond on the left or the double bond on the right. No, it doesn't matter where you put it. Let's draw that out. Okay, so we put the double bond on the left here, so we have a C double bonded to a C with a methyl group on the end. What if we drew it the other way? What if we went like this, put a double bond on the right side? That would be the exact same thing. We have a carbon with 2 hydrogens, double bonded to a carbon with 1 hydrogen, single bonded to a methyl group, a CH3. So these are the same molecules. This is the symbol sometimes you'll see for equal. Okay, these 2 molecules are the same. Either way, the isomer of cyclopropane is this double bonded CC with a methyl group. This is called propene. Propene. Propane is a 3-carbon chain. When you have a double bond, then you replace the A with an E. So this is propene instead of propane. Okay, so cyclopropane and propene are constitutional isomers. Now there is an equation that you could use to help out with some of these molecular formulas, and this is the degrees of unsaturation equation. So here's the degrees of unsaturation equation. It's 2C minus H minus X plus N plus 2 divided by 2, where C is the number of carbons, H is the number of hydrogens, N is the number of nitrogens, and X is the number of halogens. Okay? You ignore the oxygen atoms if you have any, and you ignore any sulfur atoms if you have any. Okay? Okay, so the formula is very simple to use. You just plug in the appropriate number of atoms that you have, run the numbers, and you should get a nice whole even number. Okay? Typically it'll be between 0 and then, in this class, we'll only see up to maybe 4 or 5. But you could have many, many, many degrees of unsaturation on a molecule. What exactly is a degree of unsaturation? Well, if we look back at this example, it's either a double bond. Let's go with green here. It's either a double bond or a ring system. Okay, either a double bond or a ring system. So if you have some sort of ring or if you have some sort of double bond, then you have a degree of unsaturation. So propene has 1 degree of unsaturation. Cyclopropane has 1 degree of unsaturation. Okay. And one other thing to remember for degrees of unsaturation is that if you have a triple bond, let's draw a very simple molecule here. Triple bonds count as 2 degrees of unsaturation. You essentially count beyond the normal bonding. So carbon should have a single bond between another carbon, but we have 2 extra bonds here. So this would be 2 degrees of unsaturation. Okay? So a double bond is 1 degree of unsaturation. A ring system, a ring is 1 degree of unsaturation, and a triple bond is 2 degrees of unsaturation. This is not necessary for your organic chemistry course, most likely, but it is a good equation that could be useful in some instances if you're not quite sure what a structure should be. Or say your hydrogens don't match up very well, you could always plug in to this equation and figure out if you have some sort of degree of unsaturation, be it a ring or a double bond. Okay, it doesn't tell you whether it's a ring or a double bond, it just tells you if one is present. Okay, it could be either one or both. Okay, so I'm going to draw out a couple molecular formulas here for the next question. We have CH4O, we have CH2O, and we have NH3. Okay, so you can pause the video here if you want a chance to solve it. What you want to do is you want to draw the molecule and then identify any polar covalent bonds, label the dipole, and label the partial charges on the molecule. Okay. Okay, so let's take a look at A. We have CH4O. Let's draw this molecule out. We have CO, and then we have 4 hydrogens. Let's see if that makes sense. It looks like that makes sense because we have 3 hydrogens for carbon to give it 4 bonds total. 1 bond for oxygen there to give oxygen 2 bonds, and then oxygen has 2 lone pairs. So this is methanol. Methanol, similar to ethanol, which we saw before, but methanol is just 1 carbon. Methanol. Okay, so there's the molecule. Let's identify any polar covalent bonds. Okay, first we have CH bonds starting on the left. CH bonds, remember, are nonpolar covalent. So CH bonds are nonpolar. What about the CO bond? The CO bond is a polar covalent bond. Remember, oxygen is more electronegative than carbon. So there will be induction pulling electrons towards oxygen. So there's the induction arrow. Okay, the dipole, that shows the dipole pulling towards oxygen, which gives carbon a partial positive and oxygen a partial negative. And then what about the OH bond? The OH bond is also polar. Okay, the OH bond is also polar. So oxygen is pulling electron density away from hydrogen, making this hydrogen also partially positive, and the oxygen, as before, is partially negative. Okay, so we have a partially positive carbon, we have a partially negative oxygen, and we have a partially positive hydrogen. Okay, our dipoles are being pulled towards oxygen because oxygen is the most electronegative atom here. Oxygen is pulling electron density through these single bonds, closer to itself. Okay. Now, if you didn't remember these as being polar covalent bonds, remember, you can always refer to the electronegativity chart, either in your book or online. Refer to the electronegativity chart, and you can simply compare the electronegativity difference between carbon and oxygen, and compare the electronegativity difference between oxygen and hydrogen. And you'll see in both cases, it is in our polar covalent zone, which is between 0.5 and 1.7. If it's less than 0.5, it's nonpolar. And if it's above 1.7, it would be ionic. Okay. Okay, let's look at B now. For B, we have CH2O. So let's connect C to O. And then we have 2 hydrogens. Okay, we have 2 hydrogens. Let's put the hydrogens on carbon. Now we have 1 electron left over on each atom, carbon and oxygen, which means we should have a double bond between carbon and oxygen. Okay. Now what you could do is you could plug this into the degree of unsaturation formula, and you would see that you would get a degree of unsaturation of 1. You would end up with 1 degree of unsaturation. And once you saw that, you could easily say, oh, there must be a double bond between carbon and oxygen because those are the only 2 atoms we have other than hydrogens. Okay, so that's another way you could use degrees of unsaturation to help draw this structure. Either way, here's the structure. We have C double bonded to oxygen. Now we need to identify any polar covalent bonds. Remember, the CH bonds on the left are nonpolar, but hopefully you remember from the last problem that the CO bond is polar. So let's draw a dipole arrow towards oxygen. Okay, that means carbon is partially positive, and it means oxygen is partially negative. Okay, we're pulling electron density through that CO bond towards oxygen and away from carbon. So carbon is partially positive, oxygen is partially negative. And then the last problem here, we have NH3, ammonia. Now, we only have one type of bond here, NH. So what is NH? Is NH a nonpolar bond? Is NH a polar bond? NH is a polar bond. So all of these bonds have dipoles towards nitrogen. All 3 bonds have dipoles towards nitrogen, which means all of the hydrogens here are partially positive, and the nitrogen is partially negative. Okay, again, nitrogen is the more electronegative atom. It's a polar bond, so nitrogen is pulling that electron density closer to itself, giving it a partially negative charge. Okay, so overall, identifying dipoles and partial charges is quite simple, especially once you know what your polar covalent bonds are. So the most common bonds we'll see, the most common polar bonds we'll see will be the CO, the OH, and the NH. Okay, these 3 polar bonds will be very common throughout the whole course, and we should be able to understand and identify that these are polar bonds with partial charges on either side. The more electronegative atom is partially negative, and the more electropositive atom is partially positive. Okay? We can represent this with a dipole arrow here, where the arrow points in the direction that the electrons are being pulled. And remember, we use these deltas to indicate partial charges, not a full charge, just a partial charge, where one side is partially positive and one side is partially negative. Okay. Okay, for the next question, we are going to take these 4 molecules, A through D, and we will identify all bonds in the molecule as being either covalent, polar covalent, or ionic. Okay, so pause the video here if you want a chance to solve these. And we will start with A. Let's draw this out. We have lithium connected to bromine, only 2 atoms in this molecule, lithium bromide. Now, we need to refer to our electronegativity charts if we're not sure on this. Okay, what we need to do is look up the electronegativity of lithium, look up the electronegativity of bromine, and compare those 2 numbers. Okay, we see from our chart here that lithium is 1.0, bromine is 2.8. So the difference in electronegativity between these 2, the difference is 1.8. So what would this be? This would be an ionic bond. Lithium, bromine, this is an ionic bond. And remember, ionic bonds can be written as a bond like that, or they can be written as an ion pair like this, where the lithium is positive and the bromine is negative. What about B? B, we have a few different bonds. We have Na connected to O, connected to H, NaOH. Okay, let's look up the electronegativity of sodium. So for sodium, we have an electronegativity of 0.9. For oxygen, 3.5. And for hydrogen, 2.1. Okay, so those are the three electronegativities we have, 0.9, 3.5, and 2.1. So between the sodium and the oxygen, what's the difference here? So the difference here is 2.6, I believe. 2.6, let's see, 2.6. Okay, so if we have an electronegativity difference of 2.6 between sodium and oxygen, that means that this bond between them is ionic. That's an ionic bond. And what about oxygen to hydrogen? If we remember from the last problem, this is going to be a polar bond. Let's double check that by looking at the electronegativities. So 3.5 minus 2.1, the difference between these two numbers is 1.4. So 1.4 would give us a polar will give us a polar covalent bond. Okay, so 1.4 will give us a polar covalent bond. Let's draw some arrows here. So ionic and polar covalent. Okay, I'm going to write our cutoffs here just so everyone remembers. From 0.0 up to 0.5, this is the nonpolar covalent. From 0.5 up to 1.7, that is going to be the polar. And then above 1.7 is ionic. Okay. Okay, so on the bottom here, this is our difference in electronegativity. If we're between 0.0, 0.5, this is going to be a covalent bond or a nonpolar covalent bond. If we're between 0.5 and 1.7, that's a polar covalent bond. And if we're above 1.7, that's an ionic bond. Okay, let's look at the next one. We have sodium connected to oxygen, connected to carbon, which is connected to 3 hydrogens. This is a methyl group, remember? Well, we just did sodium to oxygen. We know the difference here is 2.6. We have a difference in electronegativity of 2.6 between these two atoms. Okay, so this bond here will be ionic. And what about the CO bond? Oxygen to carbon. Hopefully we remember that's a polar bond. If we don't remember that, we can look at the electronegativities. And then the CH bonds, all 3 of these are nonpolar bonds. Nonpolar covalent bonds. Okay. Remember, our most common nonpolar covalent bonds will be CC and CH, which we will see plenty of. Almost all organic molecules will have a bunch of CC bonds and a bunch of CH bonds, okay? So the sort of interesting bonds, the ones that are going to do some chemistry for us, are typically these polar bonds and these ionic bonds because they have a difference in electronegativity, which creates some charge, either a partial charge or a full positive charge. Okay, our last one here is CH2O. We drew the structure on the last question, so I'll draw it one more time here. The CO bond is going to be polar. And then the CH bonds are both going to be nonpolar or just covalent. Okay. CO bond is polar. We should know that by now. And the CH bonds covalent or nonpolar covalent. Okay, and here's our final problem for the workshop. We have 5 different molecules here, and we are asked to identify any formal charges on these molecules, any formal charges. Okay. If you want to pause the video here and try to identify a formal charge on each molecule, you can do that now. Okay, so let's go ahead and get started with the first structure here. One thing to note before we get started is to see here that I'm drawing CH3 instead of drawing out every single hydrogen. So I'm just shorthanding by condensing the CH3, the methyl group, and writing the CH3 instead of drawing out every single bond. Okay. So we know the CH3 is fine, right? Because carbon has 4 bonds to it. Carbon should have 4 bonds to it. So these carbons are fine on the left and on the right. But the thing that should stick out to us is this oxygen here in the middle, which I'll highlight in red. This oxygen, as we remember, should have 2 bonds and 2 lone pairs, but here it has 3 bonds and 1 lone pair. So this oxygen is going to bear a formal charge. Now, what is the formal charge? Remember, we ask ourselves 2 questions. I'm going to type them up in the top right. The first question is, how many electrons should the atom have? And then the second is, how many electrons does the atom have? These are the 2 questions we need to ask ourselves when we're considering formal charge. So let's look back at this oxygen. We see the oxygen has 1, 2, 3, 4, 5 electrons. Remember, it gains 1 electron from each single bond, and then it has a lone pair. So this oxygen has 5, but it should have 6. If we recall, oxygen should have 6 valence electrons. And if you don't recall that, you can go all the way back to the periodic table, look up oxygen, see it's in group 6A, which means it has 6 valence electrons. So oxygen should have 6. Here it has 5, so it's missing an electron. So this oxygen has this oxygen has a formal charge of +1. It has a positive formal charge. This oxygen has 5 electrons. It should have 6 electrons, so we're missing 1 electron, which makes it positive. So this oxygen has a positive charge. Let's look at this nitrogen here now to the right, top middle. We have a methyl group connected to a nitrogen, which is connected to another methyl group. The nitrogen has 2 lone pairs, which is different from nitrogen's normal bonding pattern, which is 1 lone pair and 3 bonds, has 5 valence electrons. So if we look here, I drew the Lewis dot structure for nitrogen. It should have 5 electrons. Down here, it has 1, 2, 3, 4, 5, 6. Nitrogen has 6 valence electrons, which means it has an extra electron, which makes this nitrogen negative. And then looking at the top right structure, we have H connected to C, connected to an O, double bonded to an O also, but we should note that this oxygen looks a little funky on the right. We should note that this oxygen looks a little bit different on the right. It only has 1 bond to it. The oxygen on top looks to be fine. It has 2 bonds and 2 lone pairs, which it should. And then the carbon looks to be fine because it has 4 bonds, which it should. So this oxygen here is different. This oxygen has 1 bond and then 3 lone pairs. So it has a total of 1, 2, 3, 4, 5, 6, 7 electrons. So this oxygen has 7 electrons. Oxygen should have 6 electrons, but it has 7. We have an extra electron, which makes it negative. Okay. Oxygen should have 6 electrons. This oxygen has 7 electrons. So this oxygen has an extra electron, which makes it negative. Looking now at the bottom left structure, we see we have 3 methyl groups all connected to this central carbon, but this central carbon looks a little strange. It only has 3 bonds. So what's going on here? Well, remember, carbon should have 4 bonds because it has 4 valence electrons, 1, 2, 3, 4. Here, it only has 1, 2, 3. So if this carbon only has 3 electrons and it should have 4, it means we're missing an electron. If we're missing an electron, if we're missing a negative charge has gone away, that means we're positive. So this is a positively charged carbon, or a carbocation. Then for our final structure here, we can look and see that this carbon up here looks a little strange. All the other carbons have 4 bonds, which is perfectly fine. This carbon up here has 3 bonds and a lone pair. Looks like nitrogen should. So let's count up all of its valence electrons. We have 2 from the lone pair, and then 3, 4, 5, 1 from each single bond. This carbon has 5 electrons. It should have 4 electrons. This is a negatively charged carbon, or a carbanion. Okay? So applying formal charges should be quite simple if you remember these 2 questions, and you can refer to a periodic table. If you can do that, then you can easily apply a formal charge to any atom in any molecule. All you have to do is look at the periodic table and find out how many electrons should the atom have, right? Draw its Lewis dot structure, nitrogen, oxygen, carbon, whatever atom you may have. And then ask yourself, how many electrons does the atom have in this structure? Compare the 2 numbers and see if you have an extra electron or if you're missing an electron. Formal charges will only be +1 or -1. We don't have to worry about going +2, +3, +4, -2, -3, etc. Formal charge will just be a +1 or a -1. Okay. Okay, so that's all the questions I have for the first workshop. Hopefully it went smoothly for you. If it didn't go smoothly, that's okay. You can rewatch lecture 1, lecture 2, and maybe work through these workshop problems again. Work them until you understand them. These concepts won't be going away anytime soon. So as we progress through the course, all of the content that we see and learn will be built upon previous content. Okay. As you can see, we're already building on concepts from general chemistry and high school chemistry with Lewis dot structures, and we are only going to continue building on these concepts. Okay, thanks for joining me for workshop number 1. I hope you found that helpful in some way, and I will see y'all in the next one.